Okay, so before we move on to other types of operations on vectors, maybe let's review addition by working with a very simple problem. So we want to add two vectors, the vector u with coordinates 4, minus 3, and the vector v with coordinates 1 and 2. So what I want to do is do u plus v, or v plus u. That's exactly the same thing, okay, but that's what I want to do. Now, one thing to remember is that when we write u in using coordinates, we're using this duality point vector. So to each point in the plane, we can associate a vector. So when we write down u in terms of its coordinates 4 and minus 3, we assume that u starts at, well, when we're going to draw it in the plane, we assume that it starts at the origin and that it ends at the point 4, minus 3. So maybe let me draw this vector, maybe using a different color. So 4 minus 3 would be, so this is the point 4 minus 3. So I can draw a vector starting at the origin, ending here, and that's vector u. But just to be clear, it doesn't mean that this is where u is in the plane. U could be anywhere in the plane, could actually be here. But of course, here would have a different head, because it still wouldn't be at the origin. But when we write down u equals 4 minus 3, we if we want to draw it so that it ends at 4 minus 3, it must start at the origin. So you could be here, and it could be given as this vector in the plane, and v, which is the vector 1, 2. Well, if I start at the origin, move forward by 1, up by 2, this is the point 1, 2. So this is v, but maybe v could have been given to me over here in the plane, okay? But usually when we draw vectors, it's easier to have them start at the origin, because the coordinates of the vector will just tell us where the head is in that case. All right, so this is v here. Okay, now I'm going to use an algebraic approach because it's so much easier when we have vectored in coordinate form. So if I want to do u plus v, well, all I need to do is write down the coordinates and add everything component-wise. So 4 plus 1 is 5, and minus 3 plus 2 is minus 1. So I will end up with the vector 5 minus 1, which is, so this is 5 minus 1 right there. So it would be this vector. And you can see that this makes a lot of sense, because if I do u plus v geometrically, what I'm doing is I'm starting at the origin, going along u, so along this path here, and then we add v, and v is this vector right there. So u plus v does give me the vector that you see drawn in green. Okay, but usually if we're given coordinates, all we need to do is do this, and we very often won't illustrate the vectors in the plane. All right. Now, the next step is to define the difference between the two vectors. But to do this, we first need to define the 0 vector. And eventually, we're going to define the negative of a vector. And then after that, we'll be able to define clearly what the difference between the two vectors is. So what's the 0 vector? Maybe we should remind ourselves what it accomplishes with a real number. So what's 0? Well, it's a number. If I do 3 plus 0, it's a number, so that when I add it to another number, it's not changing that number. So 3, if I add 0 to it, it's not changing 3. 3 stays 3. And same goes if I do 0 plus 3, it's still 3. Okay, so the 0 vector is going to be a vector that does exactly this. Okay, so I'm trying to find a vector that I will call the 0 vector, so that when I add it to u, it's not changing u. And same goes if I do 0 plus u, it's not changing u. So what kind of vector zero, what kind of zero vector would do this? Well, let's look at the case where u is a vector in 2 space. So u would be a vector, and often we label the coordinates of a vector u with the variables u1 and u2. So those they basically mean arbitrary components for my vector u. And I want to add it to some zero vector. So that's going to be my zero vector here. Right? That's u here. So that it gives me back u1, u2. Now remember, if I'm adding two vectors, I'm going to add their components. So what does that mean? It means that when I'm going to add this component to u1, it's going to remain u1. But u1 is a real number, isn't it? So what number would I add to another real number to get back that same number? So u1 plus what will give me back u1? Well, that's easy. That's 0. If I do u1 plus 0, I get u1. If I do u2 plus 0, I get u2. So the zero vector is very simple. It's a vector with all its coordinates equal to 0. So the zero vector is basically the vector 0, 0. That's in 2 space. In 3 space, it would be 0, 0, 0, and etc. etc. if I'm in 4 space or 5 space or whatever. Okay, so that's the zero vector. If I had to draw it, it's a vector whose tail and if I draw it in terms of a position vector, its tail and its head would be both at the origin. So it's a vector that has a length of 0 and that has no special orientation or all possible orientation. It's not that important. So what you need just to remember, it's a vector that in terms of movement, it doesn't induce any movement. Okay, so that's the zero vector. After that, we can use the zero vector to define the negative of a vector. Negative of, let's say, a vector v. Okay, with let's work in R2. What's the negative of a vector? So for this, we need to remember what's the negative of a number. So when we're trying to find the negative of 3, okay, it's a number, so that if I add that number to 3, I'm going to get back the number 0. That's what the negative, this is the negative of 3 here. Of 3. Okay. Okay, so we call that number minus 3. So 3 plus minus 3 equals 0. So on the real axis, if this is 3, this is 0. Well, if I add this number that we call the negative of 3 to 3, I'm going to end up back at 0. So you can think of numbers also as vectors. Like this could be like a vector. Like my negative 3 could be associated to this vector and 3 to this vector. If I add these two together, you see I'm going to move right by 3 units and then move left by 3 units. I will end up eventually where where I started. Okay, so that's exactly the same thing, same concept in 2 space. If I wanted to find the negative of a vector, so if I have a vector, I don't know, a vector v like this, okay, what vector should I add to it to end back at the origin? Well, that's not too hard. So remember, when we're adding vectors, we're kind of following the path that we get by following each vector. So if I do v, if I want to get back to where I started, I need to go this way. Okay, so I need to go along a vector that has the same length of v, but the opposite direction. So that's how we're going to define what minus v is. So basically, if you've got a vector v like this, that would be negative v. If you've got a vector v like this, that would be negative v. Okay, very simple. In terms of its coordinates, well, that's not too hard to obtain either, because if you think of the coordinates of minus v, let's minus v, if I want to define its coordinates, I need to make it start at the origin. So minus v would be here. So imagine that v as, I don't know, maybe its coordinates are, this is 3 and 1. Well, what's the vector that's opposite to the point 3? Well, what point is opposite to the point 3, 1? That's basically going to give us the coordinates of minus v. Well, that point, well, what's the opposite of 3 and 1? It's going to be minus 3, minus 1. Okay? So maybe definition here. Okay? If v has coordinates v1, v2, then minus v, it's the negative of v, or the opposite of v, has coordinates minus v1, minus v2. Okay, super simple. And note that if I do v plus the vector minus v, I'm going to end up with the vector 0. Okay, just like this is exactly what we expect, right? This is how we constructed that negative vector so that we can reproduce something like this. Okay, with vectors. Now we're ready to define the difference between two vectors, and here's how it's gonna work out. You see with numbers, if I do 5 minus 3, a way to look at this difference between numbers is to think of it as an addition. It's 5 to which we add, so we can define a difference in terms of an addition. So it's 5 to which we add the opposite of 3. Okay, so 5 minus 3 is the same as adding to 5 the opposite of 3, so the number minus 3. So we're going to do the exact same thing with vectors. Okay, let's do this. So difference of two vectors. Okay, so if I do v, vector v plus u, okay, so the way I'm going to define this, I'm going to put a little definition on top of my equality sign, because this equality sign actually will define how, oh, I don't want to do addition, I wanted to do subtraction. So v minus u, the way it's going to be defined is that I will add to vector v the opposite of u. Okay, so this vector minus u, I will add it to v. So that's how I'm going to define the difference. Okay, so in terms of coordinates, that's also very easy to see what this is going to be like. So if I do v1, v2, let's say we're in 2 space, minus u1, u2, what does that give me according to the definition? I'm going to do v1, v2, to which I will add the opposite of u. What's the opposite of u? It's minus u1, minus u2. And now in addition is with coordinates is obtained by adding the coordinates component wise. So v1 minus u1 is going to be the coordinate of the difference of the first coordinate of the difference of the two vectors, and v2 minus u2 the second coordinate. Okay, so basically to perform the subtraction, all I need to do is subtract the coordinates. Okay, so it's very natural. So maybe a quick example, if I do the vector 3 minus 1 minus the vector 7, I don't know, minus 7 minus 4, okay, well, I need to do 3 minus 7 and minus 1 minus 4. So that's going to give me 3 plus 7 minus 1 plus 4. So I will end up with the vector 10, 3. Okay. All right. Maybe let's illustrate this on a little graph. Okay, so let's say this is vector v, and I've drawn it here in red in the Cartesian plane. And let's assume that this is u. So u is right there, and v right here. So if I want to do v minus u, it's the same thing as doing v plus the opposite of u. Now the opposite of u is the dashed vector here. This is minus u. So really when I'm adding, or when I'm taking the difference, I'm adding those, the vector v and the vector minus u. So let's do this. Now to do this, I'm going to place minus u so that it starts at the head of a vector v. So if I do this, this is minus u again, right there, okay? So actually maybe so that we can see things better, let's put it like that, minus u. So v minus u will give me another vector, which is this vector right there. That's v minus u. And that's the vector 10, 3. Indeed, you can check that this point here as coordinates. Oops. Notice that I put points surrounded by standard brackets where I used square brackets for vectors. So here I could have used either, because either it's a point or it's a vector. So both would be good here. So this is v minus u, but what I want you to realize is that this difference that we get between the two vectors, well, there's two things to realize. First of all, let's move this vector v minus u. You can see that it's also the same as this vector right there. That's v minus u. I remember vectors can be placed anywhere we want in the plane. So in fact, if I have the difference between two vectors, v minus u, if I position the vectors so that they start at the same place, right here they both start at the origin, well, v minus u will be a vector that starts at the head of u and ends at the head of v, or at the terminal point of u and that ends at the terminal point of v. So that would be true no matter what the vectors are. Okay, so maybe let me draw this here. If I have v like this and a vector u like this, well, v minus u would actually be this vector. Okay, it starts at the terminal point of u and ends at the terminal point of v. The other thing to notice is that, let's say I look at v again here. Well, this is also vector v. So the what you see here is a parallelogram, okay? And the difference between two vectors is one of the diagonal of this parallelogram. The other diagonal is the sum. So let me try to illustrate this here. So if I would do u plus v, right? Let's put v here. Okay, that's v. This creates a parallelogram. I've got this parallelogram here. Okay, so the difference v minus u is one of the diagonal, and the other diagonal is maybe let me draw it here. Is the sum. This is v plus u. Okay, so it's a neat way to remember what the difference and the sum are between two vectors. If you create a parallelogram with those two vectors, one diagonal is the sum, the other is the difference. Now, personally, I always have trouble remembering in which direction goes the difference. So when I'm given two vectors like this, okay, let's say this is uv, I'm never sure whether v minus u goes like that or like that. Okay, so instead of remembering it by heart or whatever, okay, I just remember the fact that v minus u, if I do v minus u, it's v plus the opposite of u. So all I need to do is follow the paths created by the two vectors. So v minus u, c minus u is like that. So if I do v, I follow v and then minus u, I'm going to end up with this vector here. Now this vector is the same as this. That's the difference, so that must be the difference. So then you see that v minus u, yes, it starts at the terminal point of u and it ends at the terminal point of v. This is my trick for remembering how the difference is illustrated when you're given the two vectors. Whether I'm never sure whether it goes up or this way or that way. Well, with the tricks I've just shown you, you can just recover geometrically the direction of the difference between the two vectors. Okay,